Sampling is the process of selecting observations. So we've been talking about measurement, we've been talking about operationalization. And prior to doing that, or while we're doing that, we need to understand, okay, if these are the variables and the questions that we have, and we have sort of an understanding of the units of analysis, as we talked about in the review, and the demographic of people, communities, organizations, the unit of analysis that we're interested in, we have to determine how we're going to get those observations and those metrics. So sometimes we'll be working with secondary data where sampling has already occurred and we really need to understand how that sampling has occurred because it influences our results. Or sometimes we're doing our own study, like a survey of, let's say, people on campus and dealing with college students. So we need to figure out how exactly we're going to get our observations. And a big aspect of this lecture is going to be probability sampling, which is very helpful for making generalizations and causal claims in particular, whereas non-probability sampling is not any less valid. It just creates other assumptions about our data, and we can't make generalizations as broadly. So as I have shown you this slide that we're going to be working on through the course, time and time again, we're going to come back to this slide, and we see here that right now we're dealing with the population. So who and what do we want to generalize about? We've already talked about the meaning and the concepts that we're trying to study and how to measure those things. And so sampling is, okay, how are we going to get access to that population and be able, the type of sampling determines the extent of generalizations that we can make. And now remember, generalizations are claims that we make about a population. So let's say people with higher education are 30% more likely to get X job. That's a finding. And that finding, when we're doing a study, its ability to be applied to other contexts is a generalization. Alrighty. So probability sampling in particular, as I stated prior, helps researchers generalize from observed cases to unobserved ones. So if I'm generalizing about my data, I can also generalize about data I haven't seen, but I do know if it is, if it meets probability sampling assumptions and logic, I can generalize about observations that I have not directly seen. So if we're talking about students, if I am using probability sampling across the nation, then I can make generalizations about students in general. But if I'm talking about students at a particular college campus and I didn't make generalization, or I didn't do probability sampling, then I can't make generalizations about the larger student population. And in order for probability sampling, like the basic logic behind it is representation. So each member of the population has a known and equal chance of being selected into the sample. So there are no observations that are more likely to be observed because of the structure of how we're observing things. And so this means, like when we want a representative sample, we want the sample to look like the larger population. So if the larger population of students on campus, for example, if we were doing Rutgers campus in particular, if we did probability sampling at Rutgers campus, we would have issues because Rutgers campus is not a representative population of the larger students in the entirety of the US. So for example, Rutgers is really diverse. It's one of the most diverse colleges like in the entire US. So if we were to do probability sampling at Rutgers, we would overestimate students who are people of color, students who are first generation. So we would be oversampling those specific populations, and that wouldn't be as representative of the entire college student body of the US. But if we were sampling a college campus that looked a lot like the general statistics of the population of students within the US, then that would be a representative sample. And this is because sometimes populations aren't completely homogeneous. And so our sample needs to reflect the variation of the larger population. So a big acronym that you really should know is this EPSOM. It's equal probability of selection method. And so EPSOM ensures that we're doing probability sampling. It's the core component of it. And so when we're selecting a sample in which each and every unit within the sample frame has the same or equal chance of appearing in the sample, then we're ensuring that we have equal probability of selection method. So equal probability of selection method is basically summarized by that second bullet point. And the first bullet point is talking about what I was explaining prior, that we want our sample to be representative of the larger population. So Rutgers in particular would not be representative of the larger student body population because it's too diverse, right? And other universities may have the opposite problem. It's not diverse enough, right? And so that's why we take on specific sampling strategies, which we'll get into in the next couple of slides. And so what happens when we allow equal probability of selection method, which means simple random sampling. So that means if there's equal probability, then there's a randomness that occurs for the population. And so simple random sampling is the foundation of unbiased sampling. It ensures that we are not having any error bias. And if we do simple random sampling, if we use equal probability of selection method, then that means that we can lean on statistical theorists, and you don't need to know the full statistical theory behind these assumptions. You just need to know that because we're systematically sampling in this way, we can ensure that sampling error can be quantified through confidence intervals. And we'll get more into what exactly confidence intervals are in the rest of this lecture. But sampling error, there's like a whole bunch of mathematical proofs, which you don't need to know the full extent of. But when we do these things, then there are some mathematical theory that allow us equations so we can quantify what exactly our error is. And when we quantify our error, then we can communicate that and know how much our results are likely to occur in a general population and how much of it is just due to random error. And if this all sounds like a little fuzzy, that's okay. We're going to work through it in this lecture. So a population parameter is the value for a given variable in the population. And so this population parameter is really important because it allows us sort of a metric in which we can determine whether or not our standard error, the error that we have in our sampling methods, is close to that population parameter. And the way that we understand that is through the sample statistic. And so the sample statistic, trying to get out of the way, is a summary description of a given variable in the sample. So we use the sample statistic to make estimates about the population parameter. So we never actually know what the population parameter is. We can't say it for sure, but these statistical theories allow us to say within a certain amount of confidence that we know where the population parameter is. So it's sort of like we're trying to locate something where we don't know where it is, but we get the general area of where it might be. And then we can quantify our error by the likelihood that that parameter isn't in the general area that we think it is. So this is more the mathematical theory that I was talking to that allows us to be able to make generalizations and estimate our error of our sample compared to the larger population. And so I'm just going to really read through and break down this, but you don't need to have like a super expert understanding of this. You just really need to know what the assumptions are behind this. So as we said, the key to the process of being able to estimate our error is random selection, the EPSOM, that everything has to have equal probability of being sampled. And so the purpose of sampling is to select a set of elements from a population in such a way that description of those elements, the sample statistic, accurately portray the parameters of the total population from which the elements are selected. So if we're dealing with, if we know the demographics of the larger population, that's helpful because it could help us frame how we're going to be sampling. And the theoretical understandings of this sampling distribution and quantifying error are all understanding these populations, assuming that there's an infinite sampling, that there's infinite population. And so these assumptions almost never apply in survey design. So, and there's really an oversimplification of these findings. So a lot of social research is not as not filled with error. A lot of our findings are overestimates of what actually happens in the population because we are not actually in an infinite realm of possibility where we're infinitely sampling things. And that's one of the key components of probability theory. So there are other ways there are other assumptions and frameworks to get to these generalizations that aren't based on this infinite understanding of math. And you don't necessarily need to know that, but it is good to know. And there, like an example of one is Bayesian statistics. So if you ever are really into stats and stats is your thing, that could be a space to also explore. So because of these theoretical assumptions about infinite sampling and the infinite that the populations are being infinitely sampled, and thus samples would equal 0% of the whole, that frames how we estimate sampling error. So if many independent random samples are selected from a population, the sample statistic provided by those samples will be distributed around the population parameter in a known way. So this is what I was talking about earlier, and that we don't know what the population parameter is. It's like something we're trying to locate with like echolocation, but we don't know exactly where it is. So we know a range of space in which it is. And we know the likelihood that it's in that range of space. And so probability theory, as I said before, gives us a formula to estimate that. And so statisticians have already written this math proof. You don't need to write it or understand it fully, but we use that statistical theory in order to analyze things and estimate our error. And so when we're measuring standard error using this formula, it's telling us how sample statistics will be dispersed or clustered around a population parameter. So it's telling us, okay, for the sample statistic that we're developing from our population, how likely is the population parameter to be around that cluster? So it's like sort of mapping one onto the other. And so the two key components of sampling error are confidence levels and confidence intervals. So confidence intervals and confidence levels provide the basis for determining the appropriate sample size for a study. So from this statistical, theoretical, mathematical calculations that statisticians have developed, we have these two components that, one, when we're sampling, can tell us the error, but two, can say, all right, before you sample, let's think about the confidence level that we would like, and therefore the amount of sample size that would be ideal for our particular study. And so we express the accuracy of our sample statistic in terms of the level of confidence that the statistics fall within a specified interval from the parameter. And so this specified interval from the parameter that we're talking about sort of is like part of that echolocation that I was talking about. It helps us determine within this particular range that we can understand the location of the population parameter. And so confidence levels are often put at 95%. And that's sort of random. You could do your confidence levels at other percentages, but that's just sort of a standard practice of statistical analysis, is to put your confidence level at 95%. So that range that we're speaking about is the confidence interval. So that's related to the sample statistic and where the population parameter lies. And you'd get more into this if you were taking a statistics course, a data analysis course, or a coding course, but we're not going to get super into the analysis portion. You just need to understand that as sample size increases, our margin of error is sort of reduced, and I'll show you a graph on that as well. But the takeaway that you should take away from this when you're reading literature is that all of these things have a certain amount of error in them. And you can say, depending on reading the research methods of how people have sampled their population, you can sort of argue with and point out strengths and weaknesses in sampling, which therefore allows you to point out strengths and weaknesses in the study in general and the generalization of their findings and the level of error that might be occurring due to sampling. So EPSAM is maintained through probability sampling, and these 4 types of sampling ensure that EPSAM is there and ensures that we can understand a certain amount of error and confidence in our results. And so these can be used alone or in combination, but the key feature is that the relationship between populations and sampling frames hold up to these theoretical assumptions. And so a sampling frame is a abstract list of elements from which a probability sample is selected. So it's like, if you had all the resources in the world, if you were able to observe all of the cases for the population that you're interested in, that would be the sampling frame, is this list. And it has to be feasible and within reason. And so these 4 types of sampling, the simple, stratified, systematic, and cluster, are what we're going to get into now. So simple random sampling is that each element has equal probability of being picked. Maybe they have an assigned number, and the choice for which observation gets picked is random. And this forms the basis of probability. It's the statistical tool we use to estimate population, parameters, standard error, and confidence levels. So this really is like the golden standard of sampling, but we can't always do this because it just doesn't make sense for the representation and our population, or it's just too difficult. So then comes in systematic sampling. So there's this, and we'll go back here. There's a sampling frame that is used in systematic sampling and also in simple random sampling. So the sampling frame is the full list of the observations. And when we're using simple random sampling, we're taking randomly generated, usually computers assist in that, portions of that sampling frame. And so the sampling frame, when we're using systematic sampling, is that we list 10,000 elements in our frame. So elements are part of a sampling frame. Sample element is 1 unit of that sampling frame, 1 observation of the entire list. And so if we want a portion of that element, because it's not feasible for us to observe all of them, we might do every 1,000 elements is the one we picked. But this can be difficult if there is a clear pattern in the way that that list is composed. So if we had a list of students and it was organized by grade, if we did every 1,000, maybe we might miss some grades, right? Or if we're trying to get something over time, like rainfall, if we every 10 days observe rainfall, there might be a cycle there of seasons or of like some other pattern that we're not observing and may influence and make our sample not representative because maybe we're getting too many observations that are in the spring or something like that. That's the idea of systematic sampling. Is good if you're not dealing with periodicity, which is a periodic arrangement of elements in the list, can make systematic sampling unwise. So if there is sort of a temporal pattern in your sampling frame, it would not be a good idea to go every 10 or every 1,000 sample units and pick that one. And so stratified sampling ensures that appropriate numbers are drawn from homogeneous subsets of that population. So the example I was talking about of students of college populations in general, we could get Epsom with and ensure that we have an understanding of standard error if we understand the larger student body population and then sample to get a certain amount of each of the populations that we're working with. So if the larger student body population is, let's say, I'm making this up, 40% white. If then we go onto Rutgers campus and get 40% white population, and then we do that for each race, then we may get a representative sample. And so that's a method in which we divide the larger population into subcategories, and then we make sure that the proportion of the subcategories within our sampling frame are the same as the proportion within the larger parameter. And this is helpful if we're working with things that can be measured like demographics, but it might be more difficult if we're working with things that are not measured as much in that space. Another way to do that is disproportionate stratified sampling. So we might use this if we're working with populations that are not representative of a population on some variable. So for example, we're working with criminal justice population. We might, we recognize that there is like a disproportionate amount of Indigenous people who get involved in the criminal justice population. So if we were really wanting to understand their perspective in general, we might do disproportionate stratified sampling. So multi-stage cluster sampling is when we compile a cluster. So going back, a stratified group over here, we're sort of understanding the percentages and proportionality which within the larger parameter. Then we sample it and then subsample that set. And so this may be used when it's either impossible or impractical to compile an exhaustive list of elements that compose a target population. And I'll give you a tangible example of this. In a second. So multi-stage cluster sampling with stratification. So this stratifies the sample by type and characteristic, and then from these strata, you select from the strata through simple random or systematic sampling techniques. So you can have the stratified clusters on a continuous list, and then you systematically sample from the list. So the primary goal is homogeny. So homogeny needs to make things the same, and that's a primary goal in this case. So an example of multi-stage cluster sampling with stratification is the National Crime Victimization Survey. So it's an example of multi-stage cluster sampling. And so what happens is they're trying to represent the nationwide population of people 12 and plus living in households. So rather than compiling an entire list of everyone who lives in the US, they're defining primary sampling units. So these primary sampling units are usually geographic units. And so the largest geographic areas are automatically included. Smaller ones are stratified by size, population density, reported crimes, and other variables into about 150 strata. So what we're doing is we're listing all these geographic areas, and then we are arranging them by their characteristics. And so that develops into the census enumeration districts that are selected from these PSUs, and then clusters from 4 housing units of these census enumeration districts are selected. So that's where the randomness comes in. So the first part of the sampling is to organize these geographic areas into a way where they're representative of the entire population, and to choose in a systematic way which ones get included. And then the randomness comes into, okay, if we have these smaller units, which are we picking? And that's where the randomness occurs. So I'm going to stop here and end this as probability sampling to break it down a little bit.